Hello everyone, welcome to video 2. We're going to be starting here with number 9. The key to getting number 9 correct is to notice that we have two different radicals, but we don't have too many perfect squares. So if we take the two radicals and combine them as one, and we multiply the numbers and get 48, and just like exponent rules, we add the exponents. So x to the 9th, y to the 14th. Then what we can do is re-split this into perfect and non-perfect piles with more perfect squares. The biggest perfect square that divides evenly into 48, so I know 4 goes in, but 12 can keep getting split. 16 times 3 I think is my pair. For those wondering what I'm doing, I'm only dividing 48 by perfect squares. 1 and 48, 4 and 12, 9 does not go in, 16 times 3. I know this is my pair because I can no longer keep splitting 3. Anyway, if I go back to the variables, x to the 9th is not perfect because, yes, I know that 9 is a perfect square, but x to the 9th is not perfect because this exponent must be even in order to be perfect, because you remember square root really means something to the 1/2 power, so it has to be divisible by 2. So I would split this into the closest even number, x to the 8th times x. Then the y to the 14th is perfect because it's an even exponent. So I'd have y to the 14th there. My final answer, if I reduce the perfect pile, would be 4x to the 4th, y to the 7th, square root of 3x. If we take a look here at number 10, we want to distribute the 3 root 10 into both terms, and we can multiply things that look the same. So 3 times 2 gives me 6. Root 10 times root 5 is root 50. So this would be my first term. If I distribute the 3 root 10 to the negative 10 root 2, 3 times negative 10 is negative 30. Root 10 times root 2 is root 20. Now this is not my final answer because I can keep splitting root 50 and root 20. So this would become 6 times, the biggest perfect square is 25 times 2 minus 30. Biggest perfect square that goes into 20 is 4 and then times 5. The square root of 25 is really 5, so this is really 6 times 5 root 2 minus 30 times 2 root 5. So this is 30 root 2 minus 60 root 5. And that is going to be my final answer because I cannot add something that has a root 2 with something that has a root 5. So that is my final answer for number 10. Number 11, we have a radical in the denominator, and so what we have to do is rationalize or get the radical out of the denominator. So what I would do is multiply top and bottom just by the square root of 5. I don't need to multiply by 7 because that's not a problem. So now if I multiply the top, root 3 and root 5, I'm allowed to multiply them. I'm not allowed to add them, but I can multiply them to be the square root of 15. In the denominator, I have 7 times root 25. Root 25 is really 5, so I have the square root of 15 over 7 times 5, or even better, the square root of 15 over 35. Now, as tempting as it might be to reduce 15 and 35, I cannot, because root 15 is not a like term with root 35, because the root 35 does not have a radical. So my final answer is the square root of 15 over 35. Number 12, please simplify and please no decimal answers. The goal for 12 is to see if I can combine any like terms. As of now, the root 32, the root 50, and the root 18 cannot be combined because the radicand is not the same. However, if I try to split these radicals, root 32, the biggest perfect square is 16 times 2, plus 3 times root 50, as we saw in an earlier problem, is 25 times 2, minus 2 root 18, the biggest perfect square is 9 times 2. So I can reduce all the perfect squares and get 4 root 2 plus 3 times 5 root 2 minus 2 times 3 root 2, which is 4 root 2 plus 15 root 2 minus 6 root 2. Now, because every single radicand is 2, I'm allowed to add these because they are like terms. So if I have 4 plus 15, that's 19 minus 6. So I have 13 root 2's left over. So my final answer is 13 root 2 because my radicand is the same. Number 13, again, please don't be fooled. When you see something squared, it's tempting just to square both pieces, but because this plus sign is here, it is always a good idea to write out the problem twice. 4 root 2 plus 6 root 5, and then another 4 root 2 plus 6 root 5. When I write it out this way, I notice that I have to do the distributive property or FOIL. So I have to distribute the 4 root 2 to both of these terms. So 4 root 2 times 4 root 2 is 16 root 4. 4 root 2 times 6 root 5 is 24 root 10. Switching colors. I now need to distribute this 6 root 5 to both terms. 6 root 5 times 4 root 2 is 24 root 10. 6 root 5 times another 6 root 5 is 36 root 25. I then scan this problem and I notice that both of these are like terms because the radicand is the same. So that would combine to be 48 root 10s. I also notice that the root 4 is a perfect square and the root 25 is a perfect square. So this is really 16 times 2, and this is really 36 times 5. 36 times 5 is 180. 16 times 2 is 32. I can combine the 32 and the 180 together. So far I have 212 if I add these, plus 48 root 10. Now again, even though it's really tempting to add the 212 and the 48, I cannot because this does not have a radicand of 10. It does not have a square root at all. So these are not like terms. So this is why this is my final answer for number 13. There's a lot more restrictive rules for adding and subtracting than there are for multiplying. Now number 14 has a square root in the denominator, and I notice there is a plus sign, so I'm going to need the conjugate in order to solve this one. So I'm going to write a little word conjugate here. Now I want to go back really quickly to number 11. Here I was allowed just to multiply by root 5 because there was no plus or minus. This problem, however, because I do have 4 plus root 2, we need to multiply top and bottom by 4 minus root 2 because unfortunately the root 2 is attached to the 4 in a way. So now what I have to do is I put parentheses around this, and I notice that I have to distribute the 6 into both terms. 6 times 4 are allowed to be multiplied to be 24. 6 times root 2, I cannot combine that to be root 12, so I'm going to leave it as 6 root 2. So that's my numerator. My denominator, if I distribute, I would get 4 times 4 first and get 16. 4 times negative root 2 is minus 4 root 2. Switching to this root 2, 4 times root 2 is a positive 4 root 2. Root 2 times negative root 2 is a negative root 4. And yes, I know that some of you might have already noticed that these can cancel out. You're absolutely right. That works every time when you have a conjugate. So these combine to be 0. So you have 24 minus 6 root 2 in the numerator. In the denominator, you have 16 minus 2, technically, which is 24 minus 6 root 2 over 14. And just like the quadratic formula, I can reduce this triangle by taking out a GCF of 2. So the best final answer would be 12 minus 3 root 2 all over 7. And remember, I cannot divide the root 2 by 2 because these are not like terms. Moving on to radical equations. My goal is to get the square root alone first, if possible. So I'm going to subtract the 4. Square root of 2x equals 6. I want to divide by 2, but I cannot because the radical's in the way. So let's get rid of it by squaring both sides. The inverses cross out, and you're left with 2x equals 6 squared, or 36. Now you can divide by 2, and I have an answer of 18. And I'm pretty sure that's my answer, but I'm going to go ahead and check anyway. What you always want to do is take your answer that you got and plug it into the original for x. So I think my answer is 18. So I think that 2 times 18 under the radical plus 4 outside of the radical is 10. Well, 2 times 18 is 36, so is the square root of 36 plus 4 equal to 10? Or is 6 plus 4 equal to 10? Yep, which means that x equals 18 is absolutely correct. Number 16, again, my goal is to get the radical alone, and to do so, I'm going to first move the 1 to the other side. 3 times the square root of 2x plus 5 equals 9. No, I cannot distribute the 3 in because there's no parentheses, but I do need to do something with that 3. I need to get rid of it. I don't want to square both sides yet because the radical is not alone. Square root of 2x plus 5 equals 3. I cannot move the 5, cannot move the 2 until this radical is gone because everything's stuck under there. So I'm going to square each side, have 2x plus 5 equaling 9. And now that everything's free, I'm going to solve the equation normally. Subtract my 5, get 2x equals 4, divide by 2, and get a hypothetical answer of x equals 2. If I would like to check my answer, let me write down the original problem. 2x plus 5 minus 1 equals 8. So if I take 2 and I plug it in for x, 2 times 2 plus 5 under the radical, minus 1 should be 8. Well, if I look at the radical first, that is really 4 plus 5. So the square root of 9 times 3 minus 1 should be 8. Or 3 times 3 minus 1, 9 minus 1 is 8. Check. Awesome. 2 is absolutely right. Number 17. If I would like to get anything free, I notice that nothing can be moved initially. So I'm going to square both sides of my equation. These cancel. X squared equals 11x plus 60. Now, I notice I have an x squared. And as soon as I see an x squared, I'm hoping that I can factor, not use the quadratic formula or anything. So x squared leads to factoring. It needs to be equal to 0. And I want you to keep the x squared positive if possible. So if I want to keep this positive, I'm going to move both of these things over by subtracting. So I would get x squared minus 11x minus 60 equals 0. If you want to, you can definitely write down that you're subtracting both over here, but that's up to you. Now I hope this factors. Two numbers that multiply to be negative 60 and add to be negative 11. Well, 60 is 1 times 60, 2 times 30, 3 times 20, 4 times 15, 6 times 10. This pair works. X, 4, and 15. To get negative 11, I would have negative 15 plus 4, which means two answers are either negative 4 or positive 15. Now, especially when we factor, it's very important to check. So the first thing I'm going to do is check x equals negative 4. I'm going to plug that back into the original equation, which looked like this. So, does negative 4 equal the square root of 11 times negative 4 plus 60? Or does negative 4 equal negative 44 plus 60? Does the square root of 16 equal negative 4? No, because negative 4 does not equal positive 4. So this is false, does not work, so this is out. If I check x equals 15 in the original equation, if I look at this and bring it down here, does 15 equal the square root of 11 times 15 plus 60? Well, 11 times 15 is 165 plus 60. 165 plus 60 is 225. Does the square root of 225 equal 15? Why, yes, it does. Hurrah! So x equals 15 works. Happy day. We will continue with number 18 on video number 3. Thank you.